Okay, you should have out your lecture notes for lecture 58, hypothesis testing for a difference of variances or standard deviations, the F random variable. And this is really interesting. I'm hearing an echo. I don't know if you're hearing it. But anyway, all right, to do this, we're going to have to use the F random variable, which is something we haven't looked at yet. It's a new random variable. It has 2 degrees of freedom, and you'll often see it written as F number 1, number 2, and the first one will be the first number of degrees of freedom, and the second one will be the second number of degrees of freedom. And that's just the way we write generically the F random variable with those 2 degrees of freedom. So, of course, for different numbers of degrees of freedom, we're going to have different tables. So this is one of those random variables where you can't do a lot of tail probabilities for a lot of different values of the degrees of freedom. It would fill up book after book after book. At least you can't do it in printed material such that it'd be easy to search through. But anyway, what is our curve going to look like? Well, it looks different for different numbers of degrees of freedom. For, I think if you just have a 1 degree of freedom here and 1 degree of freedom here, you get kind of an asymptotic behavior here, and it kind of swoops down like that. I'm not going to draw that one. More generically, if you have, larger than 1 here and larger than 1 here, you tend to get something kind of like that. All right, so stretches on forever, but dies off to 0 over here. That's a rough picture of what it looks like. Okay. So what do I say? Most tables give probabilities in the right table for this random variable. So I have here just a few examples. So find the right-tailed critical value for a significance level of 0.05 for F1013. Okay, so I want the first number of degrees of freedom to be 10 and the second number to be 13. And you can find a table quite easily, I think. I have one right here, and we're looking for area of 0.05 right-tailed. So let me pop this up here, and I think I have here, yes, I have right here that it's a 0.05. So I have these tail probabilities, and along the top I have the first number of degrees of freedom, so there's 10. And then down here I have the second, there's 13, so let me come down, and there I get 2.6710, right? So if this were F1013 and we had 0.05 area there, we get 0.26710. Okay, next one, find the right-tailed critical value for 0.025 for F94. All right, I'm not going to redraw it there. I'm just going to go to, we want 0.025, and I think I have it here. Yes, and we want, what is it? First number is 9, the second number is 4. So I go over to 9, and I go down to 4. Right, and 8.9047. So 8.9047 is the answer for area of 0.025 for an F94 random variable. Okay, pretty easy, right? Have to go to different tables. I had to go to the one with the area 0.025 here and 0.05 for the other problem, of course. But, so how are we going to use that? We shall use F distributions when testing hypotheses concerning the difference of 2 population standard deviations or 2 population variances. So now we're looking at differences between standard deviations or variances. The null hypothesis will always be H naught sigma 1 equals sigma 2, or sigma 1 squared equals sigma 2 squared, which is really saying the same thing. This is saying that the population variance for population 1 is the same as the population variance for the population standard deviation for population 1 is the same as the population standard deviation for population 2, and this is saying that their variances are the same. Since these are just the squares of those, the fact that this is equal is the same thing as saying that that's equal. Okay, So what will the alternative hypotheses be? Well, you'd think it would be that sigma 1 or sigma 1 squared is greater than, or maybe less than, or maybe not equal to sigma 2 or sigma 2 squared, whichever you're talking about, right? So those are the three possible alternative hypotheses: greater than, less than, or not equal to. But because of this random variable is a little bit harder to work with in terms of tables, we don't like to use all three forms of the alternative hypothesis. And what do I say here? I say, okay, I guess I make a point of that this is really the same as saying, look, if I'm saying that they're equal, I'm saying that their ratio must be 1, right? The only way you get 1 here is if this number is the same as that number, and that's the same thing as saying that. And the reason we want to think about it like this is because of the test statistic that we're going to compute, which you'll see in the next lecture, just lends itself to thinking in these terms. All right, so if I want to think of sigma 1 being less than sigma 2, this ratio has smaller over bigger. I would write it as this is less than 1. If I wanted the alternative to be sigma 1 is greater than sigma 2, I'd have bigger over smaller. This ratio would be bigger than 1. If I wanted it to be that sigma 1 is not equal to sigma 2, I would just say sigma 1 over sigma 2. If they're not the same, the ratio will not equal 1. So I could have this ratio being greater than 1, less than 1, or not equal to 1. That's another way to write the alternative hypotheses. I'm not even going to write it down here because it'll just come out a little more naturally when we do some examples. But the reason I bring this up is because, as I say here, because most tables and most software only give right-tailed critical values for f random variables, we wish to set up any hypothesis test so that it will ultimately just be a right-tailed test. So the alternative hypothesis will always be H1 is that sigma 1 is greater than sigma 2. We want to set things up, if possible, and it will always be possible, so that this is our alternative one, which would correspond to that ratio being bigger than 1, okay? We don't want to look at the other cases for the alternative hypothesis because it's hard to use the tables to gain information for those other cases. So how do we do that? What if we have something that's naturally a two-tailed test, naturally a sigma 1 not equal to sigma 2? Well, I tell you down here. We have two populations with two separate standard deviations, right? We have sigma 1 and sigma 2. We take a sample from each and compute the sample standard deviation for each sample. One of these sample standard deviations will be a little larger than the other. Whichever one is larger, we just retroactively label the population it came from as population 1. So in other words, down below here, let me, let's see. Yeah, let me rub this out. So I have my two populations, and I want to test their standard deviations or their variances against each other. What I do is I take a sample from each and compute the sample standard deviation or sample variance. One of those will be bigger for one population versus the other, correct? Whichever one is bigger, we're going to label that as population 1. So I'm always talking about testing whether sigma 1 is bigger than sigma 2. So I'm always talking about this alternative hypothesis, which is the same thing as this alternative hypothesis. So in other words, after we have done both samples and computed the sample standard deviations, whichever one is bigger, that was the sample from population 1. So we get population 1 is just what? We have sigma 1 is the population standard deviation. N1 is the sample size from population 1. And then I say S1 is sample standard deviation from pop 1, and degrees of freedom 1 will be N1 minus 1, of course. And then population 2, it's all, analogous. This is the population standard deviation. N2 is the sample size. Pop2, S2 equals sample standard deviation from pop2, and degrees of freedom 2 is N2 minus 1. Okay, and so I just say here off to the side, I have a little noting right down below. We are picking which is pop 1 and which is pop 2, which is population 2, so that S2 is greater than S1. Okay. Now, what do I say? I say by doing this, we can always make sure that the test statistic is, which is going to be S1 squared over S2 squared. We can always pick it so that it will be a right-tailed test. And we'll do some examples in the next lecture. So we're going to be looking at S1 squared over S2 squared, where you can see again, if these turn out to be equal, the ratio will be 1. But the way I've chosen it is so that S1 will always be the bigger of the two, bigger than or equal to. So I'm always going to get a number that's bigger than 1 rather than less than 1. I'm going to get the bigger of the ratio I could get than the smaller of the ratio. What this does is it means that we're always looking at the right end of the curve. Okay, so if I have my curve here, I may be looking, I may think of myself as having a two-tailed test. And of course, what does it mean to have a two-tailed test? It means that one or the other could be bigger, right? But if I always orient it so that I know I have my big one on top, I know I'm always looking at the right half of my two halves if I have a two-tailed test. So I can cut my area in half and just look at a right-tailed test. It'll make a little more sense when I do an example in the next lecture, but we'll stop here.